Hello and welcome to New York City Atheists Live on Tape, brought to you by New York City Atheists Incorporated. I'm your host, Dennis Horvitz, the David Letterman of the Hopelessly Damned. So without further ado, please welcome Richard L. BOROWSKY, Professor of Biology at NYU. We're going to find out why flying fish are lying.
Oh, I'm not going to talk about any of that.
We have evolved beyond it.
So in the last couple of minutes, I've decided that, actually half an hour or so, I've decided that this is really a tough room. It's more shaped like a bowling alley than a lecture room. This is a tough crowd. There are some things, in preparing this, I really didn't...
See what I mean?
Okay, I didn't... Gotcha. I had no idea who would be here, and I did know that there'd be various interests in educational background and so forth. I knew that not all of you would be biologists, if any of you are biologists. And therefore, and I knew that if I simply asserted things about genetics to you, you guys are not going to take it on faith, what I said. So I decided to give a rather general talk, introducing you to the cave environment, cave fishes, talk about the remarkable resemblance between unrelated species all around the world living in the same environment. It's something that's called evolutionary convergence. And so these guys here are the bread and butter of my laboratory. These are Mexican tetras. There are surface forms and cave forms there. Does everybody know which is the surface form and which is the cave form? Okay, we're on the same page for that. The beauty of this system is that these guys, while ancestral to these guys and separated by several million years of evolution, are still close enough that they can interbreed. So I can actually do genetic studies. I can cross the cave fish with the surface fish, make hybrids. The hybrids are intermediate. I take an F1 hybrid, which had a cave and surface parent, and I cross it to another F1 hybrid. I get an F2. And for those of you who remember your high school or your college genetics, or biology, you get this 1 to 2 to 1 ratio of cave homozygote, heterozygote cave surface, and surface homozygote, and that permits me to do genetic studies on these guys. Somehow, I think I can do that from here. No, I can't. So the differences between them reflect these very different environments in which they live.
Escape.
No, escape kills the whole thing. And so basically, life on the surface of Earth and life below Earth. On the surface of Earth, at least you have light 12 hours a day, and below Earth it's perpetual darkness. And the secondary effect of this is that food is plentiful, or relatively plentiful, on the surface of the Earth because you have photosynthesis. In the cave, you don't have photosynthesis. All cave ecosystems are very much attenuated because the energy input at the base is very low. Cave fish are generally the top predators. Little rinky-dinky things that can be as small as my pinky. They don't have to fear predators. There's not enough energy there to support the predator population, and generally speaking, they don't have to deal very much with competition from other species. So it's a simplified environment. It looks formidable for us. For us to live in a cave would be extremely difficult, but it actually, in some ways, is a comforting haven for cave fish. So what I decided to do today was to talk about caves in general, the cave environment, cave fish, illustrate what I mentioned to you before, this evolution to resemble one another, which is called convergence, and make a point about convergence, which is that convergence is the same as an evolutionary replication. I'm an evolutionist. I like to tease my evolutionist colleagues by telling them that evolutionary biology is really lousy science. It's crummy science compared to laboratory science. Because in laboratory science you have the replicated experiment. You have a hypothesis, you design an experiment to test the hypothesis because the hypothesis has certain predictions. You perform your experiment, it either rejects the hypothesis, the results reject the hypothesis, or conditionally you accept it, you modify the experiment, blah, blah, blah. You can do a tremendous amount with that approach. So we already know the answer to the first of them, but who are the two great biologists? Oh, and the other thing about this room is that those guys are downstairs, but that's okay. Who were the two great biologists of the 19th century? Charles Darwin and
Weizmann?
Wallace.
Gregor Mendel? Does that? I guess there can be different opinions, but I would vote for those two as the top biologists of the 19th century. I was going to say the difference between downstairs and upstairs is that they're drunk and we're sober, but now I'm not so sure. So, I'm sorry, I'm teasing you. So,
You do stand-up comedy too.
Everybody laughs at me, so that's natural-born comment. So, Mendel was the great experimentalist, and as I was discussing earlier, Mendel actually was trained as a physicist, and so he did these beautiful experiments with plants. And while Darwin was also a wonderful experimentalist and did marvelous work, we actually remember him for his observations and what he did with his observations. And this dichotomy, observationalist science in evolution, experimental science, and just about all other aspects of science, this dichotomy exists today. So there are lots of extremely important things that happened in the history of life. Insects, for example, developed a waterproof cuticle. And that waterproof cuticle permitted them to go all over the land. Just about every landmass that's not frozen perpetually has insects on it because they don't dry out. Birds develop feathered flight. The amniote egg was developed. Amphibians have to go back to water to breed, but reptiles, birds, and mammals don't have to. So extraordinarily important changes in the history of life, but these were events that happened only one time. And because they happened only one time, if you have any idea, any hypothesis about them, you have no independent data set to test your hypothesis. But with cavefish, there are 100 species of cavefish around the world that are known, probably many more to discover, and every one of them is a replicate of an experiment that asks what happens when you turn out the lights and limit the amount of food. So I think this aspect here, convergence equals evolutionary replication, is rather important. Darwin knew about cavefish, but was really puzzled and incorrect in his interpretation of the loss of their eyes. And so we'll talk a little bit about Darwin's dilemma. I want to speak as well about how we can do genetic manipulations, simple hybridization of different cavefish populations and restore vision. So things that have come from populations that have been in the dark for 1 million years and probably for most of that 1 million years couldn't even see. In one generation of hybridization we can make hybrids that do see. And then if we get to it, and because I was told 30 or 40 minutes, maybe we won't get to it, I want to talk about natural selection against eyes and also sleep. One of the things about cavefish that we've discovered is they don't really sleep very much. So this shows the entrance to a cave in northwest Thailand. I'm one of these little specks down here. It's an extraordinary through cave. The river goes in one side of the mountain, comes out the other side of the mountain. This is the side that it comes out. I've been there about 3 or 4 times, and every time I go there I end up sleeping exhausted on that rock at night, because to walk down from that breakdown pile is dangerous. It's odd that it should be dangerous to walk down a pile of rocks at night if you've just been caving, but somehow we feel that. This is in the cave. some distance away, looking back at that big pile of rocks there. And all caves, of course, have entrances, and in the entrance there's light. And if the cave is really a short run through a mountain, then you really don't have blind cave fishes in it. It has to be a longer run through the mountain. This is a cave that's only about 1 kilometer long from this entrance to the exit. We looked for cave fish there, again in northwest Thailand. Found none. Lots of surface fish, though. Not every cave can be walked into, and so this is Vasquez Cave, a map of Vasquez in Mexico. The fish I wanted are down here. That's 915 feet down, and you do that on ropes. It will not be very effective to play it this way. Just shows my former graduate student Luis setting ropes in one of the caves there, and there was a soundtrack here, which I don't think we'll hear. Had I known he was going to do this, I would not have permitted him to do this.
What's he doing?
He's setting the rope, and what he says now is rope down. And what you do to get those fish, and these are the Mexican fish that I work on, is simply rappel into the cave. And climb up. It's the climbing up that's the hard part. Without a soundtrack, there's probably little point in playing this further. That's my present graduate student, Martina Bradic. She's rappelling into that same cave a number of years later, getting set to rappel in. She had absolutely no experience at doing this. We trained her. That's ain't gonna work anyway. Thank you. We trained her. This was the first pitch she dropped, 68 meters on a half-inch thick rope. And to give her some confidence, what we did is we did some politicking in town and got the roof of the fire department to practice rappelling techniques. This is a flowstone formation in Melana Cave in Thailand. The riverbed is here. The main river flows through the mountain from one side to the other, but there are internal tributaries that leave a flowstone deposit. And on the top, in the gores, the little holes on top, you find one species of cave fish, and actually over here in the water that's dripping off, there's another species of cave fish. An absolutely extraordinary animal. This is the animal. It's about that long, 2 inches long maybe. It has these extraordinary pectoral and pelvic fins that it can use to stay in place in the most rapidly moving water. It has no melanin pigmentation. It has no visible eyes. I've sectioned these fish. I can find actually no evidence in the adult of any eyes. It's extremely unusual for a cave fish. Most of them, even as adults, have small residual eyes. This shows the animal in nature. The other was in an ashtray in the lodge before we sacrificed it. This shows an animal in nature, just maintaining its place in the thin stream of water that's flowing by. This is my student Luis again, the one setting the rope in Mexico, and here we're looking for Cryptotora in rapids. And this shows, without the soundtrack, it shows the animal holding its own in rapidly moving water. And this one, maybe the quality of the video isn't good, but it really does climb waterfalls. It's just quite extraordinary. Has no competitors, and what it eats, we think, are just bacterial slime. So, switching continents, this is a cave catfish. It has tiny little eye spots. It doesn't respond to light behaviorally. You can flash a bright light on it, it doesn't respond to it. It's also very light in color. This guy, or female, this fish, is also about the size of the other one. This comes from Brazil. So I have good colleagues and good relationships with people in Brazil, in Thailand, and Mexico, and these are the places where I do my work. This shows another species, also Brazilian, not quite as light in color, filmed in the cave. The water it's dealing with isn't moving quite as quickly as the water that Cryptotora dealt with, but these guys are quite capable of exploiting the environment that they're found in and where they live, and have a characteristic look that all of us know denotes that they're cave fish. And then the final few examples, this is a karst formation in central Thailand. It's overlain by harder rock, which is how it's survived, whereas everything around it has been eroded away. And there are caves in this formation, and we've collected different species of cave fish there. Some of them are completely eyeless, or at least externally eyeless. Some of them of the same species have small eye spots, non-functional. But all these fish I've shown you may have a little bit of yellow coloration or pink coloration, but they tend to lack melanin, and they certainly lack a visual system. And that, of course, comes about from the environment in which we live, but there are questions about exactly what were the forces driving the evolution of this eyeless condition. And just to make the point that there are certain other interesting aspects of these caves. Lots of the caves in Thailand and some in Mexico have bad air, so you're breathing 4 or 5% carbon dioxide and existing on 17% oxygen, which is actually not so hard to do. It's a little bit painful, but if you're not exercising hard, it's okay. If, however, you repel into it, you really find it very, very difficult to climb out of it. And this is Jerry Campbell, who's in charge of caving safety. I say he's going the extra mile right before we enter one of these caves. Was that a grr I heard? I forgot for a moment who I was talking to. Well, that's Jerry's thing. Cave fish exhibit this convergence in loss of eyes, in loss of pigmentation, and in other characters. They've changed, it's not as obvious, but they've changed their metabolism. They're far more efficient, because if there's not much food around, you really better be able to make the maximum use of what you can get. And I guess this will be the final final slide on convergence. So the bread and butter species, these Mexican cave fish, come from this area in Mexico and are found in, they're not all shown here, but 29 different caves in this area over 140 kilometers from here, the northernmost cave, to the southernmost cave. They actually have derived from at least 2 separate species of surface fish that have been in the area. There was one set of surface fish that inhabited the streams around these caves and gave rise to populations over here. Then they went locally extinct. Another one came in and gave rise to populations here and there. So independent invasions. This is an old slide. I say 4 separate origins. We now know it's 5. Independent invasions, independent stocks, and yet they all converged on very much the same phenotype, the same look. One of the convergences, remarkably enough, is for sleep. So this is a record of activity of animals, of 4 different groups of animals, over a 2-day period. So the daylight, 12 hours, nighttime, 12 hours, the second day, 12 hours, second night, 12 hours. And what's plotted here is the amount of activity, the amount of inactivity, sleep, during 10-minute periods throughout this time period. And you can see that in black, surface fish sleep at night. Most of those 10 minutes at night are spent not moving, sleeping. Same for the second night here. They sleep much less during the day, although they seem to take the Mexican fish. They seem to take a siesta around midday. And in colors, red, whatever this is, gold and blue, we have the same record, same type of record for three different species, three independent populations of cavefish. They all have very much reduced amount of sleep. Here is a bar graph. Surface fish sleep 800 minutes a day, and the three independently derived populations of cavefish sleep 200 or 100 minutes a day. We don't really know why this is the case. We think that if you're in an environment where there's not much food and you can't predict when the food will come by, you better be awake when it does come by in order to get it. But that's just a hypothesis. We haven't tested that yet. So it's not only eyes and pigmentation, it's metabolism, it's behavior, it's lots of things that have changed. Am I speaking too long? Okay. So as was shown in the previous graph, for sleep, we're looking at three different independently derived cave populations of the same species where you have convergence. And the convergence is shown here. Here's a fish from Molino Cave, most northernmost of these Mexican caves that have cavefish. And then here's one from the Patron population. These guys are albino, these guys are albino. These guys are completely blind. These guys are completely blind. They both have very small residual eyes, or I'm sorry, I'm searching for a term, but that'll do. Sunken deep in the head, and they certainly look very much alike. I can actually tell the difference between them when they're swimming around in the tank, but you probably would not be able to. So this convergence that I speak about is really very well exhibited by this group. And I think this is the point I made in the introduction. I meant to make it here. Convergence is to evolutionary biology as replication is to experimental science. 100 different species of cavefish is 100 replicates of the same experiment. One species with 29 populations, that's 29 replicates of the same experiment, where because they all came from the same species of surface fish, you have a better idea of what their genetics is. So, Darwin. Darwin, when he wrote The Origin, knew about cavefish. He also knew about cave salamanders from Slovenia, but in the United States, there's a group of cavefish that had just been discovered, and obviously these were of great interest to him. He knew, as well as everybody did, everybody believed in evolution or change through time, he knew that they had descended from surface fish. And so he knew the polarity of the change, and what he's saying here, much more eloquently than I could say it, is if you poke my eyes out and put me in a cave, if you put me in a cave, I can't see. If you poke my eyes out, I can't fail to see any more efficiently than I failed to see when I had my eyes. It's dark in a cave. So he's saying, I can't see how eyes are injurious to animals living in darkness, and he knew nothing about genetics. He had actually been mailed a copy of the journal that had Mendel's paper in it, but he never actually read that paper. And so he simply had to attribute the loss wholly to disuse. We now know, of course, much more about genetics, so we know about genetics, and we know from Darwin about natural selection, and we know other means, not driven by natural selection, by which a character can, that isn't needed, can degenerate. And so there's some residual debate as to whether eyes are selected against in the dark, or not having a function. There's natural selection will not be policing and screening new mutations that come along. So new mutations might come along not be selected for, but just by chance increase in frequency in the population, and structure tends to run downhill if it's not tended. The metaphor I used before was the metaphor of the untended house. If I move away from my house for 20 years and nobody's watching it, I mean, I know for sure when I come back there'll be window panes broken, there'll be leaks in the pipes, there'll be squirrels in the roof, there'll be there are squirrels in the roof. But what I don't know is where these window panes will be. I don't know which tiles or shingles will be pulled up by the squirrels and so forth and so on. So if natural selection is not policing a phenotype, keeping it up to snuff, keeping it up to par because it's needed, in this case because it's not needed, then things can go downhill. That's called genetic drift as opposed to natural selection. So major questions, I'm not sure I'll cover them directly, but if it is selection, how? Referencing Darwin's dilemma, I don't really understand it, he said. Mutation, is it random mutation, is it drift? I've explained it all. And one of the things that we're interested in as well is how many genes have been changed between being an eyed surface animal and a cave fish. Is it one gene that's knocked out, or 2 genes, or 10 genes? Before we started this research, nobody actually knew. Now we know it's probably on the order of 10, 12 genes per population.